Today in class 12th, I am taking the topic the motion of a charged particle in the magnetic field, the Lorentz force. So when a charged particle moves in the magnetic field, a force acts on it, which is called the magnetic force or the Lorentz force. Since this force was given by the Lorentz, so after his name, it is called the Lorentz force. When a charged particle moves in a magnetic field, a force acts on it. It is called magnetic force or Lorentz force. Let a charge particle is moving with velocity v in uniform magnetic field B at angle theta. It means that this is now suppose the magnetic field B here. This is now a charged particle moving with velocity v. This is now charged particle q. This angle is theta. Then the force on it. This is now the force F. So force F equal to Q V cross B. This is called the Lorentz force or the magnetic force. Here we neglect the electric force. So we assume that there is only the magnetic force. So now this F equal to QVB sin theta into n cap. This is not like this. N cap is the unit vector. Where n cap unit vector perpendicular to both B and V. So this gives you the direction of the magnetic field. So taking the magnitude, this is equal to your Q V B sin theta into n cap. Then this F equal to Q V B sin theta. This is not so much. So now from here you can see that this magnetic force depends upon the magnitude of the charge, the velocity, the magnetic field and the angle between them. So you can see from here that for neutral particles, like neutron, atom, molecule, etc. The charge, the F is equal to 0 because there is no charge on these particles, as Q is equal to 0. Now the direction of this force is given by the Fleming's left-hand rule. This is the Fleming's left-hand rule. This forefinger and the middle finger and this thumb are stretched perpendicular to each other in such a way that this forefinger represents the direction of the magnetic field and this middle finger the direction of the particle moving with velocity v. Then this thumb will be the direction of the force. So this force is always perpendicular to both the magnetic field and the velocity. The direction of force is always perpendicular to plane containing the vectors V and B. This direction is given by Fleming's left-hand rule. Given by Fleming's left-hand rule. Left-hand rule. So now we can have the special cases of this force F. So this I have told that when the particle is neutral or it carries no charge, then the magnetic field, then this magnetic force will always be equal to 0. Now the special cases. Special cases. Now suppose this particle is not the neutral, even the force may be 0, it may be maximum, it may be minimum. So you can see that first if theta is equal to 0 degree. 0 degree means that the charge is moving parallel to the magnetic field. So V and V are parallel. V parallel to B. This is no situation. Then B, this force F is equal to Q, V, V. Sin 0 and sin 0 is equal to 0. So this force is equal to 0. This is the minimum force. Minimum force. So minimum force of the minimum Lorentz force will be equal to 0, but this will take place when the charge is moving parallel to the magnetic field. This means when this angle is theta or angle is equal to 0 degree or 180 degree, in both the cases this will be always to be equal to 0 or 180 degree. So in this case the particle moves in a straight line. The path of charged particle is a straight line. So sometimes this is asked that if suppose the charged particle is moving the magnetic field such that the force is 0, then what will be the path of the particle? So this will be a straight line. And now second. Now you can have that if theta equal to 90 degree or pi by 2 radian. It means that this beam is perpendicular to B. So they are mutually perpendicular to each other. In such a case, F equal to Q V B sin pi by 2, and this is equal to Q V B. This is the maximum force. So this force is maximum, and when this particle velocity is perpendicular to the magnetic field, then the particle does not move in a straight line, but it moves in a circular path. The particle moves in a circular path. So what will happen? That this force, magnetic force, that provides the necessary centripetal force to the particle, the Lorentz force, provides necessary centripetal force to the particle. It means what? That suppose this is the magnetic field here. This is the magnetic field B, and suppose particle is moving perpendicular to this one. This is now your particle Q moving with velocity V, so that this angle between them is equal to pi by 2 in pi by 2. Then this particle moves like this. It will move in this way. So this is now your center. Let this is now radius R. So it has the velocity perpendicular to this one. This is now V, here also. This is now velocity. Then the force will act towards the center. This is now center, O. So the force acts towards the center. This is the centripetal force. So centripetal force is how much? Force Fc is equal to mv square upon r. R equal to radius of circular path. Radius of circular path. Then in equilibrium, now this F equal to Fc. So this is now your Q V B equal to mv square upon r, and you know that this one V will cancel from here, so this will give you a relation that this radius is equal to mv upon q. So you see from here that this radius depends upon the linear momentum of the particle, the charge of the particle, and the magnitude of the this magnetic field B. So for large value of this R, this mv must be maximum, the linear momentum must be maximum, charge must be small, and magnetic field must be small. So R equal to P upon QP. P upon Q, where P equal to mv, the linear moment. The linear moment. So what we have? Clearly, this R is proportional to P, and this R is proportional to 1 upon Q, and this R is proportional to 1 upon V. So these are the three factors upon which this radius depends. So for larger value of this R, P must be larger, Q must be small, V must be small. Therefore, for large value of R, the momentum P should be large and Q and B must be small. Must be small. So this radius is dependent upon the mass of the particle, velocity of the particle, and that the charge of the particle, and B, the magnetic field on the where this particle is moving. So now you can have now time period T equal to 2 pi r upon what? The velocity v. So now this you can have this T equal to 2 pi upon v, and in place of r we write down this mv upon qv. Now this b and b cancel, so we get it this T equal to 2 pi n upon qv. And if you want to find out the frequency, n equal to 1 upon t. This is now equal to 1 upon t. Like this, so we will have this n equal to qv upon 2 pi n. So now what you see that this time period and the frequency are the independent of the velocity of the particle. Whether a particle is moving fast or this is moving slow, the time period and the frequency will be the same. The time period and frequency does not depend upon velocity of particle. So what we have, that is T proportional to V raised to power 0. This is independent of this one. So this T and N both depend upon the mass and the charge and the magnetic field. So these three quantities are associated with this frequency. Now you can find the angular frequency also. Angular frequency. Omega, this is equal to 2 pi n. This is not 2 pi, and n is equal to qv upon 2 pi m. So this 2 pi and 2 pi will cancel. So omega equal to qv upon m. This is not so much. So thus we see that when the particle is moving perpendicular to the magnetic field, then we are having the time period and the frequency, and also this omega is independent of the velocity. So omega is proportional to v raised to power 0. This does not depend upon the velocity of the particle. It is depending upon the charge, the magnetic field, and the mass of the particle. So this is when the particle is moving at right angle to the direction of the magnetic field. Now if suppose the particle is moving at angle theta, that is neither equal to 0 degree nor this is 90 degree, somewhere else between 0 and 90 degree, then what will happen? What is the path of the particle? So now we are at the case number 3. When theta is greater than 0 degree and less than 5 degree, the path of particle, will be helical or spiral. Spiral. Now then this is like this one. This is the magnetic field B. The particle is moving like this. This is now Q. This angle is theta. Then what will happen that this will move in this way. So this is like this one. In this. This is the helical path. इसे हम कहते हैं कुंडली नुमा पथ. कुंडली नुमा पथ. So this is what that this is now velocity V. Then we can have the two components of velocity. Now this is magnetic field B and this is now velocity. This angle is theta. Then we can have one component along this one. This is now your V cos theta. And another component is to like this. This is now your V cos theta. V sin theta. So components of the velocity. Of V. ये कौन सा है ना this V parallel. This is equal to V cos theta. And this V perpendicular. This is now your V sin theta. So V parallel is the component that is parallel to this magnetic field. And perpendicular means the component which is perpendicular to this magnetic field. This is now your V sin theta. So this V cos theta component gives the straight line motion, but V sin theta gives the circular motion. So the path of the particle is neither a straight line nor a circular path, but this is the helical path. The component V parallel gives a straight line path and component B perpendicular provides circular path. The combined effect of these two of these two is that particle moves neither neither a straight line nor circular path neither in straight line nor in circular path nor in circular path, but it moves in helical path. Helical path. So this is like this one. So what we have, that this component gives the translatory motion and this component gives the circular motion. So the effect of these two, that particle is neither moving in the translational motion nor in the circular motion, but it is the combined effect of these two is that this is moving in the helical path. So now let us find the radius. Now this Lorentz force F equal to Q V B sin theta, and since this is moving circular path also, so this is the centripetal force. So centripetal force Fc, this is equal to your this MB. So now we'll have this V sin theta whole square upon R. So in equilibrium, now this F equal to Fc. So this is now your Q V B sin theta equal to MV sin theta whole square upon R. So you can find that this R equal to MB sin theta upon this is now your QB. This is now radius. The circular path will have so much radius. You are seeing that this is dependent upon this, the value theta, and you can see that when theta equal to pi by 2, then this R is equal to MB upon QB. So for theta equal to pi by 2, this R equal to MB upon QB. This is what that I have told you earlier also. Now if we want to take the time period, T equal to 2 pi R upon, this is now your V sin theta. So this is T equal to 2 pi upon V sin theta, and R is equal to MV sin theta upon QB. So now this V sin theta will cancel, so we will have this T equal to 2 pi M upon QB. This is not so much. So this is the time taken in one circular path when this is making one circle. t equal to so much, then pitch. So this pitch, it is the distance moved by particle in one time period. So this is the straight line distance. So definitely this will be provided by the B parallel component. It is due to B cos theta component. So this x equal to what we are having, this B cos theta into t, the time period. So this x equal to B cos theta into time period is now 2 pi m upon qb. So we can have this x equal to 2 pi mb cos theta upon q. Now you can clearly see from here that just like this one, for theta equal to pi by 2, if we take theta equal to pi by 2 here, then this x equal to 0. So for theta equal to pi by 2, x is equal to 0. And for theta equal to 0 degree, this x equal to 2 pi m v upon q. This is like this. So you can see that when the particle is moving perpendicular to the magnetic field, it is not following the straight line, but this is now in circular path. And when the particle is not perpendicular, but this is parallel to the magnetic field, then this is moving the straight line. Moving in a straight line. So this you can see that for a particular case, theta equal to 0 degree, or this is then this x is maximum. So this is the minimum value, and this is maximum value. So thus we can see that when the particle moves at an angle theta with the magnetic field, then it follows the helical path. Also you can find this frequency also, and we are looking from here that this t is independent of the velocity. This is just like when the particle is moving perpendicular to the magnetic field. So this time period and the frequency does not depend upon the velocity of the particle. Angular frequency omega is equal to 2 pi upon t. So this omega is equal to 2 pi, t equal to 2 pi m upon qb. This is not like this. So this omega equal to qb upon m. This is not angular frequency. So these are the special cases when theta is equal to 0 degree, theta equal to 90 degree, and theta is neither 0 nor 90 degree, then we are having the different paths. So this is all about the motion of the charged particle in the magnetic field and the Lorentz force. This Lorentz force is also called the magnetic force because this is provided by the magnetic field. So this force is called the magnetic force. So thank you very much.